What I aim to do in this short videotape presentation is to illustrate three things. First of all, to show you a general purpose computer model of pharmacokinetics, which is of absolutely generalized kind. Then to show you a computer simulation of breathing in human subjects. And thirdly, to show you how it is possible to embrace a teaching program using the breathing model within a text reading system operated by a general purpose driver. And as you see, I'm sitting here at a VT100 terminal, which is connected in fact to a DEC computer, one of 25 terminals running off an 1144. But these programs are written in standard Fortran and will run anywhere. Now here's a diagram of the pharmacokinetic model, and we've got a central plasma compartment which can be fed intravenously or from an intramuscular depot or by mouth, PO, per oris. And we've also got other compartments in which the plasma equilibrates, that is to say an interstitial or intracellular compartment, a lipid compartment, and of course a liver which metabolizes the drug, kidneys which excrete it, and a stomach and intestine through which it's absorbed. Well, that's the basic structure, and here is an introduction to the model on the screen. I'm going to type my name for future reference and then ask for a normal young adult male volunteer. Now I'm going to give a prescription. Now let's consider what we might give. We'll try something simple, say kanamycin 250 milligrams intramuscularly. I'm going to give this to this normal young adult male volunteer around about average height, 70 kilograms in weight. So I'm typing in at the bottom of the screen now kanamycin 250 milligrams intramuscularly. But I haven't, of course, specified whether this is a stat or repeated dose. So I've got to get that right and specify that, and as soon as I have an acceptable prescription, and that is now accepted, I can now sign my name indicating, or initials indicating that's all. Now let's just select a suitable type of run. So I'm going to ask for 1 to change, and I'm going to change the type of run, type 2. Let's ask for a 6-hour run. The current run is 12 hours. We'll have 1 graphs of total plasma drug concentration. We'll plot output every 30 minutes, and we'll have the output presented at the visual display unit. Now just before we run, we'll just store this with the store instruction and store the present state so we can come back to it in a minute. Now let's just ask for continue to run for the specified 6 hours. Now here we've got a vertical graph coming out, and across the top of the graph you see the scale, a logarithmic scale of drug concentration in milligrams per litre. And starting from the origin at 8 o'clock in the morning, we have 0 concentration of kanamycin, and then as over the 6 hours we have a sudden rise and a gradual fall as the drug is excreted. And at the end we can ask for inspect, and we can look at the amount of drug in different compartments. And as you see, if you remember this for future reference, the plasma concentration at the end of 6 hours is 2.9 odd milligrams per 100 ml, milligrams per litre rather, of kanamycin. Now let's just backtrack to our last stored state and alter something. Now the obvious thing to alter here is the condition of the patient. We can alter a number of patient factors. There are some 30 or 40 patient factors. Let's alter the glomerular filtration rate from 7.5 litres per hour, which is about 120 mils per minute, and make that 1/10 of that, 0.75, to illustrate the effect of severe renal failure. And now continue. We shall then get exactly the same vertical graph coming out against time, if I press continue. But this time we've got the presence of chronic renal failure, and at the end of 6 hours or so, instead of having 2.9 odd, we've obviously got something approaching 10. If we look at the inspect, we see the amount of the plasma at the end of 6 hours is 8.6 milligrams per litre, some 3 times what there was before. Now let's backtrack once more to our previous stored state and make a different change. Now let's give the same prescription of 250 milligrams of kanamycin, but this time by the intravenous route, and we'll sign that prescription and run that same prescription with the same time scale. And this time, of course, the sudden intravenous bolus has shot the plasma concentration right off to the right of the scale, off scale, and caused transient nausea. But of course the drug has been excreted rather faster, so the slope down here is faster. And if we inspect, we'll find instead of 2.9 at the end of 6 hours, we've only got 2.18 left. So this illustrates the way in which different routes of drug administration can be studied. Now let's look at the effect of a completely different subject of the same type of prescription. Instead of a normal young adult male volunteer, we'll ask to specify our own patient, and we'll specify a small child, a male child, 100 centimeters long, weight 20 kilograms, and age 3. And we'll give that same prescription as we gave initially, which you remember finished up with, at the end of 6 hours, some 2.9 milligrams per litre of kanamycin. And we've now altered all the sizes of the body compartments, which have been automatically altered. And when we're just giving the same type of run as before, 6 hours, with graphs of total plasma drug concentration, plotting output every 30 minutes. When we run that, we shall of course expect to find, and will find, a much higher concentration, you see, with some symptoms, and indeed a dangerously high concentration of kanamycin, because the compartments into which the drug has been given were very much smaller, and the results show a plasma concentration of 26 instead of 2.9. If we want to look at the drugs available in the current version of the model, you'll see there are quite a range of drugs available, and in addition to single drugs, we can also in many cases study sequential and parallel metabolites, which are identified with an M at the end of the name, and we can study these simultaneously. But I haven't chosen to do this on this particular demonstration tape. I just really wanted to give the flavor of this pharmacokinetic model. Well, now I'm going to turn to another model which has in common a rather similar type of presentation, but is in fact a model of human respiration, as you will see in this diagram. And this program allows us to study the way in which a number of factors interreact in the control of breathing and in the determination of gas tensions in the arteries, the tissues, and in the lungs. What you have in front of you here is a schematic diagram of some of the more important components in this model of human respiration. In the center of the picture you will see the lung cage containing the heart and a lung. There are arteries conveying blood round to the tissues where gas exchange takes place. The brain is sitting on the top, controlling everything, getting impulses and information from chemoreceptors and from the arterial gas tensions reaching it. And then there are other things we have to think about, such as, for example, the amount of dead space and the tissue metabolic rate and many other factors. Well, now let's turn to an actual run to give you the flavor of this particular model, so-called MacPuff, for quick reference. Now, I don't know whether you're more familiar with SI units or millimeters of mercury. Personally, I prefer millimeters of mercury as I'm more used to them, so I'm going to operate the model in that unit, those units. And here I've brought up a new subject, and here we have various values appropriate for an average normal human subject. Along the top we've got a scale of 0 to 120 millimeters of mercury, and the symbol C marks the PCO2, symbol O the PO2, the symbol V the total ventilation in liters per minute. And below this you see a table of various values. Here, for instance, is the arterial pH, 7.4, the PCO2, 39, PO2, 93, respiratory rate, 12.7, total ventilation, 6.1 liters per minute, and various other things. And we've got a number of factors we can change, 30 factors. I'm going to change the inspired oxygen, and to change this, make a really spectacular change and make the value 0, so to simulate the breathing of pure nitrogen without any oxygen at all. And now give a run. We are warning the patient won't like this much. Now if we just stop the run here, you'll see the PO2 has come shooting down, and after 30 seconds or so it's only about 20 millimeters of mercury. And that has stimulated breathing and ventilation. The symbols V here at the left have moved up, and as ventilation has been increased by the chemoreceptors, it's rising, you see, and then that has blown off CO2, so PCO2 has come down. And at the end of a minute of half a minute or so, we've got a PCO2 of 32. The pH has gone up 7.45, as you might expect. The total ventilation is increased to 29 liters per minute because breathing's been stimulated. The patient is very blue. Now let's continue, and here we have a deteriorating situation. Ventilation has now stopped at a minute and a half or so because the brain is now out of oxygen. The PO2 is very low, it's 10, 11 millimeters of mercury. The PCO2 is rising, and if we continue, the PCO2, which of course had been lowered by the hyperventilation, is beginning to rise, and if we continue it will rise still further. The patient is quite unrousable and very blue at this stage. Breathing has stopped, and of course, although the arterial gas tensions are staying the same, or not much different, the PCO2 slowly rising, things are deteriorating pretty severely in the tissues and the brain. So let's consider what we might do at this stage. We could make some change or continue just as we like. If things pass out of range compatible with life, then our patient or simulated patient will die. If we continue, you'll see the PCO2 rising slowly, and the things obviously are not going to go on for very much longer. So let's put the patient now back on 100% oxygen and see what happens. No better. Of course, for the very obvious reason the patient's not breathing, and so the oxygen can't get in. So now let's specify some artificial ventilation. Ventilation rate 15 cycles per minute at 300 cc's tidal volume with no positive end expiratory pressure, and give that a run for half a minute or so. And what happens? The PO2 goes quickly off scale. It's now 150 millimeters of mercury. The patient is fighting the ventilator because of retained CO2. He feels better. To get back to normal now, we really need to go back and change now to natural ventilation so as to allow the patient to reach a steady state. If we look at what's going on inside, we can see a substantial lactic acidosis has developed. This gives the gas tensions and amounts in all the different compartments. Plasma lactate concentration, as you saw, has gone up from 1 to 6.8. Now let's go to natural ventilation. We'll change something, change natural artificial, and specify now return to natural ventilation. And we should now, if we continue, see the CO2 blown off and things settle down to a steady state, and the patient feels better and things are returning to normal. The PO2, you see, is 622. Well, now I'd like to illustrate the way in which such a model can be presented within the context of a teaching program called MacAid. Now, we haven't written this exercise, so I'm going to create a text, a teaching text online, and we've got to think of a name for it. Let's call it, say, Teach 1 DAT. Now, this is a teaching file which doesn't yet exist. I'm now going to type the authoring password, author, which allows me to create a text file on the system. Now, there's a menu of things we can do. We can generate new frames, which is the only worthwhile thing to do at this stage because we've got no existing frames to display and there's nothing to edit or renumber or run. So we'll ask to generate new frames, and here we've got various types of frame. If we type the letter twice, we get the details of what the particular frame does. This is a description of what an exercise consists of sequentially numbered frames or nodes, and the first line of each frame has got coded instructions followed by text. So let's have a text introduction to our exercise. We don't know what the frame number will be, but the MacAid generator system inserts this automatically. We won't worry about cursor controls, nor about the score or the sum. One can keep running scores, running totals of what's going on. Now let's enter some text. This is the intro text. We can also run, of course, lowercase. I shan't type anymore, and we terminate that with a double slash. We're not sure what the destination frame number is. Down the bottom of the screen we've got we can actually inspect what's going on, but let's just press the return for default and transfer control to the next frame number. Now let's have a question frame now and ask a question. We're not going to worry again about cursor, scores or anything else, and we'll just ask a question. Let's say, are you ready? That's all we need to ask, so we terminate that. Now we can branch by user input, and we are expecting some text reply rather than numeric reply, so we're hoping for the answer yes. We'll put yes first. And what number are we going to branch to? Well, perhaps the next one in sequence would be 30, would follow frame 20. So that's an instruction to go to yes if to 30 if yes is typed. Now we could envisage other answers like no, and we might want just to give a feedback message and repeat the question. So here's a feedback message. You are feeble. So if the user now types no, we are expecting to insert the message at the screen, you are feeble, and then the question will be repeated. We have also to envisage that there might be some reply other than yes or no, and if we want to allow for this, we can ask again for a text entry and just press return, and that gives any text entry other than yes or no, and we perhaps will give a appropriate feedback message for this, which is don't be silly. Misspelt, I notice. So far so good. Now let's stop. That's our question frame. Now let's insert a little text to follow. The computer has inserted frames 21 and 22 in between frames 20 and 30. Now we'll insert a little text, frame 30. Just to mark where we are. And we'll now illustrate the way we can link up the subroutine I've just showed you, the model of breathing, and call it up by instructions from the text file. Now to show the effect of breathing nitrogen in a model of human breathing. So let's return to the menu and ask for a subroutine frame. Now we want to call up the model. Again, we'll just type a default frame number. We won't worry about score, but we'll enter subroutine 3, which is the code for the respiratory model that I demonstrated just a short while back. And the text now will be instructions to the model. Now, naught instructs the model, don't print anything. 2 says run in millimeters of mercury. Then switch on with 1.7. And then to change factor 1, which was the inspired oxygen, and make this equal to 0 to give the effect of running on nitrogen alone, and then 2 for continue. So now we've got instructions to the model to set itself up and run an experiment giving 100% nitrogen to breathe. Now let's insert a little bit more text, and this will be in frame 50, the next frame in sequence. So we'll just insert another text frame, just pressing return to get default parameters. We'll make a note where we are. We have now reached frame 50, and now let's run a different experiment. Instead of 0% oxygen, we'll look at 10% oxygen, which will obviously give a different result when the model actually runs. And the destination frame number we'll put in by default, which will be the next one in sequence, which is 60. Now let's insert another subroutine frame, type S. Again, we'll ask for subroutine 3, the same subroutine, but we could of course call a different one if we wanted. And this time we'll give a set of instructions exactly the same as in the last example, but this time we'll specify 10 instead of 0 for the percentage of oxygen. And then a default next frame number automatically inserted, and then we'll want to end up the exercise at this point. We'll put in a final text frame. This is the end. Destination frame 80, and then if we want the generator to exit automatically, we can just put in an end frame wherever we want to finish the exercise and return control. Now we've generated a text exercise, and we can now edit this exercise by use of various editing commands which we can run online. I've asked to list from frame 10 16 lines, and this is the text file that we've actually built up. You see, frame 10, this is the intro text, I shan't type any more, followed by the question frame, followed by 2 return frames for the 2 messages in response to no and other replies, another text frame, and then at the bottom the first S or subroutine frame with the instructions to the model. Now if this is not what we want, we can edit it if we want and change things. That's the second subroutine frame, frame 60, frame 70, frame 80. So now we've built up a text file which looks the way you've just seen it. If we don't like it, we can change things. Here is the text of frame 20, the text of frame 21, the text of frame 22. Silly is misspelt there. So if I want to modify the first line after 21, I can run the cursor along and just delete the incorrect character, and we've now permanently changed the text file by the use of this simple editor. Now we're back to the master menu. If we actually run the exercise and press the command Go, you will see the introductory text typed on the screen. If I press return, we go on to the next frame, which was the question frame. If I type author, I can go back if I see a mistake and edit it, and if we modify frame 10, the second line, we can correct that misspelling of type and insert an inverted comma and then go once more. Now that is now correctly spelt, and we can continue. Are you ready? If I just say Y, I get the corrective message. If I say anything other than yes or no, I get the corrective message. If I say yes, now we get the introduction to show you the effect of breathing nitrogen in a model of human breathing. And when I press return, we call the subroutine in automatically, and as you see, the instructions were just given automatically from the text file to the subroutine, specifying the run that I showed you earlier when we were just examining the model. And we have all the results which you will remember from last time. Now, as soon as the user can, of course, stay with the model, but as soon as he If he presses continue, he continues the run that you remember with breathing stops, but any time he can come out of the model by just pressing stop. And now he's back in the text file. We've now reached frame 50, and we're going to look at the effect by contrast of breathing 10% oxygen. If I want to edit at this stage, I can just stop any moment, edit frame 40, from frame 40, and look at the instructions to the text file. If I wanted to change that 0, I could modify it and change it to something else. So I can modify the instructions, and I can modify the instructions to the subroutine, and I can modify the text exactly as I want to. And so I can slip in and out of the editor and go back and run the program. So if I now go back to running frame 50 and now press return, now here is the effect of breathing 10% oxygen, not 0% oxygen, and of course we have a much lower fall of PO2 and a much less serious situation, though the brain is of course quite low in oxygen, and various oscillations and so on are taking place. So in this illustration I've shown you how you can build up a text exercise and run a complicated model, and as we're running it we can slip all the time in and out of the editor and change anything we like. Here, if we look at frame 10 again, frame 20, frame 21, frame 22, frame 30. Here's show was misspelt, so we'll just correct that and delete that misletter, and then we can go back into the exercise and go at the start with our corrections. And that was the same run as you've just seen. So now we'll stop. If we press return again, now we have 10% oxygen, and we now stop. Well, I hope I've been able to give you some flavour of the way in which a computer model can be embedded in the text of a teaching exercise in a completely flexible way. And the generating system which I've illustrated, to run MacAid we have described as MacGen. This and all the other programs that I've illustrated in this tape are all written in standard Fortran and are all available for distribution to educational institutions.